All right, y'all. So here we go through some of these questions that I assigned on worksheet 4. Worksheet 4 was graphing, but we have to set up our function and factor a little bit. So I'm going to go through and do some of these problems here with you. I'll go through pretty slow on some of these the first time we go through them, and then as we get into some of these problems that repeat throughout the homework, I'll probably take a little bit less time. But looking here at number 8, what it's first asking us to do is set up this right here, f times g of x. Now that dot there, it does mean multiply, so we're not setting up our composition of functions. We're really just setting up what's f of x times g of x. So all we do there is we take whatever f of x is, multiply it to g of x. So we're going to do x times negative 3x squared plus 12. So this is what it will look like, x times negative 3x squared plus 12. Now since we're multiplying to a binomial, something that has two terms, we do need to make sure we put some parentheses around that. That's what our function is. That's setting up f times g of x. So I'm going to take that off to the side here, and we'll work over here. Okay, now it's at this point where there's a couple different ways you can go. You could distribute this x through, but our goal here is to factor, right? So if we're factoring, let's just look at what can we factor. So you look at this, negative 3x squared plus 12, and the question is, can we factor that? The answer is yeah. Negative 3x squared and 12, we can factor that using the greatest common factor, right? Negative 3x squared and 12, they have two things in common. Not only do they have this 3 in common, where we can divide them both by a 3, but the other thing is, since this negative 3x squared is negative, that first term is negative, we're going to take that negative 3 out as well. Okay, so we're going to factor out a negative 3. That's our greatest common factor. What we have left over in the parentheses is, dividing out the negative 3, we're left with an x squared. 12 divided by negative 3 is negative 4, with still this x out in front. Now keep in mind, these are being multiplied together. We could just write that as negative 3x. But we can actually go further, right? X squared minus 4, you look at that, that's a difference of perfect squares. Again, that's when I would set this up and ask, what to the second power is x squared? Well, that's x. What to the second power is 4? That's 2, which allows us to break that down further into x plus 2, x minus 2, with this negative 3x still tagging along out in front. That is completely factored. Right now, it's from that form right there that we can move on. Right now, we have this completely factored form. We're actually supposed to graph it. So we set this up. Now we have our opportunity to graph it. So let's start with our end behaviors. Right, for the end behavior, we take that term of highest degree from each factor. So the negative 3x, the x, and that x, from those three factors, we multiply them together. That gives us negative 3x cubed. From that, we know that the degree is 3. The leading coefficient is negative 3, telling us that the right side has to go down. Leading coefficient is negative. The left side goes up. Odd degree means they go in opposite directions. Okay, our end behaviors are done. Now let's move on to our x-intercepts. Okay, to find our x-intercepts, right, that's when we look at each of our individual factors there, and we'll set them equal to 0. So negative 3x equals 0, x plus 2 equals 0, x minus 2 equals 0. X plus 2 equals 0, x minus 2 equals 0. Solve each of those. On this, negative 3x equals 0, we divide by negative 3, so that tells us that x equals 0 there. Subtract 2 here, we get x equals negative 2. Add 2 for that last one, and we get x equals positive 2, giving us 3 x-intercepts. Now the last thing we want to know about the x-intercepts is it going to bounce off the x-axis or is it going to pass through? And that's when we look at the multiplicity. Again, that's what's the exponent attached to these x's here, and they're all to the first power. They all have an odd multiplicity, telling us that for each of these, we're passing through it. So when you see an even exponent, that's when we bounce. So we can put those on our graph. 0, -2, and +2. And I'm just going to label that they're all passing. Now the last thing we do have to do is find the y-intercept. The nice thing about this problem is anytime you have an x-intercept at 0, your y-intercept is automatically at 0, 0. I'm going to say because x-intercept at 0. Anytime you have an x-intercept at 0, your y-intercept automatically becomes 0, 0. You do have to say the y-intercept 0, 0 and go there on your graph and label it. Now with all of that done, we can go through and graph our function here. So we start with the end behavior. What we know is the left side goes up. So from that farthest left point, make sure your graph goes up. And then we're following our directions. We get to this x-intercept, we pass through the x-axis. So we're going to go through that point down into the bottom 2 quadrants. Make sure you come back to this x-intercept here at 0. Again, we're passing through, so we're going to go into those upper 2 quadrants. Doesn't matter how far up you go there. Just make sure you come back to the last x-intercept there at +2. Again, we're passing through, so we go into the bottom 2 quadrants. And we end up with something that looks like that, where the right end behavior is going down. Checks out with our end behaviors from the beginning. So it takes a little bit of work there, but just make sure you're taking your time as you go through and graph these problems. Alright y'all, so here we go. Number 10, I'm going to take a little bit of a different route just to show you there's a couple different ways you could go about doing these problems. Now it starts out the same way as that last problem, where we're going to do f of x times g of x. That's what that's telling us right there. So f of x times g of x. Again, what that looks like is we're going to do 2x times this 2x cubed minus 50x, which again, that just means we could set it up like that. It's distributing. Now the difference is, what we did on that first problem is I factored this first. What we could do is take that 2x and multiply it in first. That might be a little bit easier. We end up getting 2x times 2x cubed is 4x to the 4th. 2x times 50x is 100x squared. Okay, that would be it multiplied out. Now I'm going to take that up to the side and we can look at that. Again, I'll show why this was beneficial here in a second. But we still need to go through those steps of factoring. Right, so we look at this, 4x squared to the 4th minus 100x squared, and we want to start with the greatest common factor. What do they have in common? Well, 4 and 100, we can divide them both by 4. We could take an x squared out of both of them. So that 4x squared comes out in front, and what's left over is going to go inside the parentheses. So we take out 4x squared from 4x to the 4th. The 4 is gone, we're left with 2 x's, so x squared. We're dividing 100 by 4, that gives us 25. We took out the x squared, so there's no x's left. We can go one step further, just like we did on that last one. This is our difference of squares. X to the 2nd power is x squared, 5 to the 2nd power is 25. That allows us to break that into x plus 5, x minus 5, with that 4x squared still tagging along in front. That's completely factored, now we can graph. Now, why that was beneficial is because when we're graphing, the 3 things we need are end behavior, the x-intercepts, and the y-intercept. We start with the end behavior and watch what happens here. To find our end behavior, we can use any of these equations here. Any step of these works because they're all representing the same equation. The easiest place that we could look is right here at this first step. That's in standard form. To find our end behavior, we need our degree and leading coefficient, right? Our degree, highest exponent you see, is 4. Leading coefficient is also 4, telling us leading coefficient is positive, the right side goes up. Degree is even, the left side also goes up. So it's pretty quick because we see it in standard form. Now, just to prove that we're doing the same thing, if we were finding the degree in this form, factored form, we take each individual term of highest degree from each factor and multiply them. 4x squared times x gives us 4x to the 4th power, which is that same leading term there. Right? So we're still looking at the same thing, giving us the same end behaviors. But that finishes off our degree and leading coefficient, which now we know our end behaviors are left up, right up. What we're going to move into now is the second step, is finding our x-intercepts. Again, to find the x-intercepts, you set each of these independent factors here equal to 0. X plus 5 equals 0, x minus 5 equals 0. And we should be able to solve those. All these ones on the right are quick. 5 and negative 5. This one here on the left, just don't overcomplicate it. You divide by 4, you get x squared equals 0. This is telling us that x has to equal 0. Anytime you end up with this factor out in front that has an x, it's giving us an x-intercept at 0. Now the last thing we need for our x-intercepts are they going to bounce or are they going to pass through those x-intercepts? And again, what we're looking at is the multiplicity. What's that exponent attached to the factor? So we look at 4x squared. It has that exponent of 2. Even exponents mean that we're going to bounce, right? Multiplicity of 2 bounces. 5 and negative 5, however, for these two factors here, there's no exponent, telling us that it has a multiplicity of 1 for both of them, which means that both of these x-intercepts were passing through the x-axis. And from that right there, we can put our graph our x-intercepts. We have one at 0, and at 0 we know that it's bouncing. We have one at negative 5, and at negative 5 we know that it's passing through. And we have one at positive 5 that's also passing through. Now, very similar to our last problem, we end up with this x-intercept that's at 0, this point right here. Again, anytime you have an x-intercept at 0, your y-intercept automatically is 0, 0. So there's no work that has to be done there. You could plug in 0 for x, and you'll end up getting 0, 0 no matter what. Again, you do need to make sure you label that on the graph. After that, we're just graphing, so follow what our end behaviors say. What we know is that the left side goes up, so that farthest left point, we need to make it go up. We come to this point here at negative 5, and we're passing through the x-axis, so we go from that top two quadrants to the bottom two, go down however far you want, make sure you come back to the x-intercept at 0. You're bouncing, so instead of passing through, we're going to bounce right back down, right? We came from the bottom, we end up going to the bottom. We come back to this last x-intercept here at 5. We're passing through. We're going from those bottom two quadrants into the top two quadrants, ending up with that shape there. Again, this is just a different way of doing it. You could, at this point right here, factor out a 2 and an x and get you to this step here a little bit faster, but then you don't get to see that standard form. Either way works. Whichever one you feel more comfortable with, you can use. All right, so here's number 11 from that homework. Gets a little bit different. Now it's telling us to set up f of x minus g of x. And this is just a little trick that you have to be careful of. When you're doing f of x minus g of x, you're doing 2x cubed minus everything from g of x. Why that matters is because when you're setting this up, it's going to be 2x cubed minus 12x, because we're distributing that negative through, but that negative switches that to a positive 18x. Okay, that's what our equation should look like, right? Subtracting is going to subtract everything from g of x. That's our starting equation there. Let me bring that up. 2x cubed minus 12x squared plus 18x. And that's our equation. Again, that's in standard form. There's no parentheses, which is nice because eventually we're doing our degree and leading coefficient. Degree is 3, leading coefficient's 2. It's really quick when it's in standard form. But what we need to do here is factor. So the first step to factoring, again, is always GCF. What do they have in common? All of these you can divide by a 2, and all of these have an x in common. That 2x we can pull out in front. What's going to be left over is, if we factor out 2x, we should be left with the x squared. Factor out 2x from this, we're left with the 6x. And factor out 2x from this last one, we're left with a 9. But we're not done. We have to go as far as we can. x squared minus 6x plus 9, we can factor that. That's a trinomial. That's when we're going to use our area model, right? So just real quick off to the side, I'm going to set that up. The x squared in the upper left, the 9, positive 9 in the bottom right. To fill in those two missing boxes there, we're looking for two numbers that multiply to 9 and add or have a sum of -6. Those two numbers are -3 and -3. So -3x, -3x fills in our area model there, and now we're doing the greatest common factors. So x squared and 3x have an x in common, -3 and 9 have a -3 in common. X squared and -3x have an x in common, -3 and -9 have a -3 in common, giving us our two factors of x minus 3 and x minus 3 with that 2x in front. Now we can go a little bit further here. We can make this a little more simplified by combining those x minus 3's. We can say that's just x minus 3 to the second power, and now that's everything that we need. It's completely factored. We should be able to graph that. So start with the end behaviors. Again, you can either choose to do it in this situation here with the 2x times the x squared and get 2x to the third power, or you could look right up there at that leading term in standard form, and that'll tell you the degree and leading coefficient as well. We're still looking at the 2x cubed no matter what. What that tells us is the degree is 3, leading coefficient is +2. The leading coefficient is +2, the right side goes up. If the degree is 3, it's odd. The left side goes down in an opposite direction. Okay. Now we move on to our x-intercepts. Again, for our x-intercepts, we set each factor equal to 0. There's two factors here. We got 2x equals 0. We have x minus 3 equals 0. 2x equals 0, that's going to tell us that x is equal to 0. X minus 3 is an x-intercept at +3. We go through, we need to graph our x-intercepts, but what we care about is at those x-intercepts pass through or bounce off the x-axis. For x equals 0, that's a 2x. It has an exponent of 1, multiplicity of 1, meaning that we pass through. Where the x minus 3 has this exponent of 2 here, telling us that it has a multiplicity of 2, which means we're bouncing at that x-intercept of 3. Let's put those on our graph. X-intercept here at 0, and it's passing through. X-intercept over here at 3, and it's bouncing. Again, to finish this off, it happens again that our y-intercept ends up being 0, 0, because we have this x-intercept here at 0. This point right here, x-intercept being at 0 forces the y-intercept to be 0, 0. Again, make sure that you label that on your graph. And we can graph it to finish it off. So start with the end behaviors. The left side goes down, so I'm going to start with that farthest left point going down. We get to that x-intercept at 0, 0. We're passing through, so since it was in the bottom two quadrants, we're going to pass through and go into the top two quadrants. Come back to this x-intercept here at 3. We're bouncing, so instead of going down to the bottom two quadrants, we shoot back up to the top two quadrants, and it looks something like that. Finishing off that graph for number 11. Okay, so here's number 12. This is the last one I'm going to do with you. If you have any questions on it, feel free to come into my office hours or send me an email so I could help you out. But on number 12, they just give us our equation here in standard form, so we can start going through and factoring this to find where the x-intercepts are. Again, the first thing you need to do is factor, and by looking at this, what I notice is there's an x in all of these, so we have a greatest common factor here of x, but specifically, this has 4 x's, this has 3 x's, this has 4 x's, this has 3, this last one has 2, meaning we can take 2 x's out of all of those. So that's our greatest common factor. Also, because this leading term has a negative, we're going to factor out a negative x squared because it's going to make our lives a whole heck of a lot easier. So that negative x squared as the GCF is going to sit out in front. And what's going to be left over is we take out x squared from x to the fourth, we're left with x squared. The negative is just going to change all of these signs here to positives as we write them in our parentheses. The negative 4x cubed, when we take out the x squared, is left with a 4x, and that last one is left with a positive 4. Again, because we're dividing each of these by negative x squared. Okay, now we can go a little bit further here. We can factor this trinomial using our area model. So write that out real quick. That's an x squared, that's a positive 4. So what we need to do is find two numbers that multiply. So they multiply to 4 and they have a sum of 4. That's pretty quick. Those two numbers are 2 and 2. Allowing us to finish off this area model here with 2x and 2x. And now you're doing greatest common factor of columns and rows. X squared and 2x have an x in common. 2x and 4 have a positive 2 in common. X squared and 2x have an x in common. 2x and 4 have a positive 2 in common. Giving us our factors of x plus 2 and x plus 2 with that negative x squared out in front. Now we're almost done. We can go one step further here. X plus 2 and x plus 2, let's combine those and write it as x plus 2 to the second power. Now I'm going to take that and we can work with that for the rest of our graph. Alright, first thing, end behaviors. Right? To find our end behavior, the easiest place to look is when it was in standard form right here. That's the leading term. The highest exponent is 4, so the degree is 4. The leading coefficient is negative, which is all that matters. Leading coefficient is negative, the right side goes down. Degree is 4, they go in the same direction, the left side goes down. End behavior is done. Now if you did it when it was in factor form here, you would have done x squared times x squared, that's a negative x squared, whoops, sorry, that was a negative this whole time, negative x squared times x squared, which is negative x to the fourth. I just forgot to carry that negative along, just be careful, because obviously I made a quick error too. But you still get that negative x to the fourth, telling you that the right side's down, the left side's down. Okay, it's a negative. Now, x-intercepts. To find the x-intercepts, you set each factor equal to 0. So negative x squared equals 0. X plus 2 equals 0. This one's quick, it's x equals negative 2. This one's a little bit trickier, but not really. You divide by a negative 1, giving you x squared equals 0, still telling you that x equals 0 there. Determine if we pass through or bounce for these x-intercepts. If you look at both of them have this exponent of 2 telling us that they both have a multiplicity of 2. Even multiplicity means that we're bouncing at both of those x-intercepts. So we have an x-intercept at 0 and at negative 2 that are both bouncing because they have that even multiplicity, or they were represented twice when it was in its factored form. Right? That's what an even multiplicity is. You see x plus 2 twice. Now, to finish it off, you do need to find that y-intercept. The y-intercept, however, ends up being 0, 0 one last time here because we have this x-intercept here at 0, automatically forcing it to 0, 0. Make sure you label it. And we can go ahead and graph this. So we'll use what we know. The left side goes down, so that farthest left point needs to go down. We get to this x-intercept here at negative 2. We're bouncing, so we hit that x-intercept and we go right back down. Stay in those bottom two quadrants. Make sure you come back to that x-intercept there at 0. Again, we're bouncing, so we go right back down to those bottom two quadrants, and we finally end up with that graph that looks like an M. So I can say da 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 da. Sorry, I'm not sponsored by McDonald's, but if they want to sponsor me, go ahead. Okay, I'm done messing around there. We're good though because the right side is going down as well. Now there's a couple of extension questions here, which is fine, right? They're quick. How many x-intercepts are there? That's easy, right? Look at how many x-intercepts did we end up with? 1, 2. Look at your graph. 1, 2. Those are your x-intercepts. There's 2 of them. How many relative minimum or maximums are there? Sorry, relative maximum is when it goes from increasing to decreasing. Those are like the peaks of our mountains, right? How many times does that happen? Once there, it goes from increasing to decreasing. Once here, it goes from increasing to decreasing. So there's 2 relative maximums. Now it's not because that's where x-intercepts are. That just happens to be where it switches from increasing to decreasing. And one last one. How many relative minimums are there? That's decreasing to increasing. Again, that's going to look the other way like that, where it's a valley. Where does that happen? Right here. Look at decreasing to increasing. There's that switch. Right there would be a relative minimum. So there's one of those. Finishing off that problem there, I know these take a little bit of effort, but take your time. Make sure you can factor, and if you can factor, which is why we spent so much time on it there in Unit 2, you should be able to get to these answers here at the end. If you have questions, again, send me an email, reach out to me, and I'd be glad to help you.